Howdy, everybody. I'm here for day 9 of Advent of Code. I've been having a lot of fun. I did have a couple days where I was sick and I just didn't feel like really doing much, but I've been able to catch up. So I am caught up as of right now. Day 10, I finished. So you'll also see a video out on that. Um, I probably the live solves. I imagine I'll maybe try and do them on the weekend, but I'll also do a summary video like this so you can just kind of, if you just want to know how I solved it and not me trying to fumble through it. I feel like the going through it maybe is more helpful. Like I'm hoping it's like a teaching experience. It's good. I think it's good to see people fumble through it because you'll understand like, oh, even though this guy has like, 30 years of experience or whatever, it's not 30, but like 25 years of experience, he still has to think through the problem. He makes mistakes. He has bugs. Those are all very normal things to happen, right? So I think those are good, but at the same time, it's a little hard to do those things, especially when you've got families and jobs and stuff like that. If I can just spend like a half hour here and a half hour there and not sit down the whole time and then just do a recap, that's easier. But maybe on the weekends we can try and do that. We'll see. So, day 9, this was the disk defragmenter. And this one was interesting to me because it kind of uh there's a kind of a known algorithm called the two pointer problem where you kind of are tracking two pointers. Sometimes they're following each other and growing. I think we've actually seen that in videos. There's like a tortoise and the hare one to find cycles where you use that. There's also one where you like go into until you meet them, and that's what this one was. So again, this is sort of a brute force problem for the day. I mean, how many ways can you say we brute force these? I think it's just to say that if you know kind of like a tricky algorithm like the two pointer, how to use two pointers, this one's not really hard to do. And I mean, technically it is. You're just trying all the solutions. Just you're doing it in a somewhat efficient way. But the idea is you're just defragmenting a disk. So they're going to give you a list of strings, and that's the disk map. And the idea is the first, all of the every other one starting from the first is a file, and every other one starting from the second is a free space. So that is to say, there's a file of size 2, and then there's a free space of size 3, and then a file of size 3, a free space of size 3, file of size 1, free space of size 3. I think they show it down here. Yeah, here's the example, right? So you can see like you can see how here's the three parts of free space, and here's the file, and so on and so forth, right? So I think this properly illustrates it. And then they just say each of the files have a unique ID. So like this file right here has an ID of 0, and it just increments from there. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can see how that is a unique ID. The gotcha here is this input is small enough that there's only 9 files, so you stop at 9. But printing like this may not be helpful when you're debugging if you've done this before, because I mean, the input size is much larger, right? And so your unique IDs are going to be multi-digits, but they may not, span large spaces enough to show those. So this is a good way to, like, I think, visualize it for a small example. But just remember, these IDs can get relatively large, and so you just have to remember, like, these 2 bits are owned, or blocks are owned by the file 0. These 3 are owned by file 1. And you'll get way down here and you'll say like, oh, these 4 are owned by file 98 or whatever, right? And so what they want to do is defrag. And for part 1, they just want you to move 1 block at a time. So what does that entail? And they say from the end. Basically what that means is take the 9 and find the leftmost free space and put it there. Take the next 9 leftmost, put it there. And the 8 leftmost and put it there, and just continue doing that. So you can see how this is kind of a 2-pointer problem. Here's their example. If you have a pointer that starts here where your free space is, and then a pointer where the thing you're trying to move is, eventually those 2 pointers will move up, right? As they're moving in towards each other. You'll have a 9 moved and then another 9 moved, and slowly you'll eventually get to the point where the 2 meet up and there's no more space, and now you're defragmented. So the idea here is you're just doing it 1 bit at a time, moving them over, and you're moving these values. And then it says, and then like how do you know if you've solved it correctly? You use these values here and create a checksum. Basically, you multiply the block ID by its position in the disk to get your value, right? So that's what this is talking about here. And so what it gives you is it say based on the input, defrag your disk, and then do a checksum on it and return that checksum. What is that checksum? So my first question was how big is this, right? Do I need to do this more efficiently at all? I didn't necessarily feel like I had to, because to be honest, I couldn't come up with like a much better solution. But you can actually see here in my code, I actually looked, I was like, hey, how big is this thing going to be? So I'll run it. And it was like, okay, there's going to be a total of 95,000 items in the array, right? Like my concern was based on, I mean, the input is really large, right? But you can see each of the numbers are relatively small. And so the idea was, okay, well, I'm never going to use more than like 100,000. My vector's never going to be more than 100,000 values long, right? So I'm like, okay, clearly I can just do the 2-pointer system, and there wasn't any trick to it. That was the thing that was going through my mind is there a trick that I need to look for? But because it was small enough, I said to myself, I probably don't need a trick. So how do I build the disk? Here's me trying to be Mr. Functional, and I think it looks okay. Basically, the idea is I'm going to go through the input and all the characters. I want to skip white space. I'm going to convert it to a digit because that's going to give me the size, right? The size, if the number's a 3, that means that file size is 3, or that free disk space is 3. So I'm going to convert it to a digit, map it to a U size because I'm using indexes, so I want to use a U size, and 2-digit returns a U32. So I just convert it to a U size. I think on most systems U64 is what a U size is, but anyway, so I convert it to there. Then I enumerate it because I need to know what position I am in the array to get the ID of it, and then I can just turn that into a vector and flatten it out. Is what's happening here. So for example, for the first element, if I get a 2 and it's 0, I know I need to make a bunch of zeros 2 times. And then for the next one, it's going to be free space. So I'm going to make a bunch of empty ones that many times, right? And then I just flatten all those together and collect them up. So what's going to happen, what I quite literally get is something like this, but in a vector in Rust. And these dots represent none, and these values represent some and the ID. And that's all that I'm really putting in there. The sum and none using an option, my thinking was that's an easy way for me to figure where the free space is, right? But you can imagine, like in memory, essentially what I've done is created this, but just as a vector with all the unique IDs being these values here. Okay. So now I just use the 2 pointers to start moving forward, right? So I know I'm going to start the left at 0 and the right at the end of the array, and I'm just going to keep looping until they equal each other, right? Until they meet, essentially, is the way to do it. So I want to find the next free space, and so I just keep looping and incrementing the left until I find one that's empty, right? So I say while left is less than right and disk left is some, right? There's something in there. I can just start incrementing there. I just keep incrementing. So at this point, I've now found an empty slot. And then I just do the same thing on the right hand side, right? I'm going to slowly move in until I find one that's not empty. And so now at this point, I have values that are, I have one spot on the left side that's free and one on the right side that's not free, right? And that's what, and so like you can imagine at this initial position right here, it's this right here on the left hand side and this right here on the right hand side. And so I can just swap those values, right? And so that's literally what I do. I just swap the two values, and then I increment and decrement the pointers, right? So now I move my left to here, or I guess to right here, and my right to here, and then I just start over again, right? I just say, okay, now I'm gonna loop again and find the leftmost free space and the rightmost non-free space, swap those, and increment and decrement, and keep doing that. And so you just keep doing this, and it looks exactly like this. If you were to like look at the memory every single time, it's just going to go blop, 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 and then eventually you're done. So to solve part one, once you've got that disk like defragmented, what you need to do is do that checksum. And if you remember what they said was, it's basically just the multiple of the ID and the its position on the disk. So I can just iterate over the disk and enumerate it and then multiply those together if there's a value in there, right? If nothing's in there, I can return 0 or ignore it. That's what this filter map does. But otherwise, I just multiply the position by the value, by its ID, and sum those together, and that gives me part one, which is this right here. So it is a very large number, and using a usize was relatively important here. Like, I don't think this would fit in an actual U32. I haven't checked exactly, but I don't think it would. Anyway, this one wasn't hard because you basically just have 2 pointers and you're moving in and solving the problem. What part 2 said was, okay, that's really good, but now you've got cases where, like, for example, 8 here is now sitting in between 1. And so you can see, like, part of 8 is now fragmented between the file 1. And so what they'd like to do is only move to do the same thing, but move the entire file and only move it where there is some free space. So I had a bunch of thoughts going through here. You can technically, there are some things called like a segment tree that I thought about briefly. But at the time I was sick and I didn't really want to implement a segment tree. The way that a segment tree works is you build this tree that helps you see where there's like free space. And thinking about it now, I'm not totally sure it would be helpful for this problem, because what the segment tree is really good at is saying, is 5 in one of the segments, and it will say yes or no. I guess you could maybe do it with the free space. But you could say like, hey, what is the distance between 2 and 3? You might be able to say, oh, it's 3. It just didn't feel like it was going to be any more efficient, right? Because the idea is, if you look at what they want you to do, it's the same thing. You just now have to say, oh, I can now move the 9 over to here, and that leaves 1 free space. But I can't move the 8 over there because it's stuck. And actually, as you go through all of it, you'll see, oh, there's no place for me to move an 8. But I can move the 7 right here. But now I can't move the 6 or the 5. But I can move the 4 right here. Right? And so this is as defragmented as you can get it, because you're moving whole blocks, whole files. And so, again, looking at the segment tree as a solution, there's also like the potential to say, could you use the 2-pointer system with this value right here, but just find all the 9s? And I think I saw some people that solved it that way, right? Is they basically said, okay, if I'm right here, I want to find all of them that have the same value. And now I start here and say, can I find a space with 2? And if I can, then I can move it. So you think about it's like a two-pointer system, but then you do some extra work to find how big the file is, and then do some extra work to say, can I find a place to put that file? So it's almost like I don't know, a four-pointer system, because you have two that always track like where you are to start with, and then how you move within those things. What was easier for me was to just say, well, what if I just treat these sections as blocks and then just do the two-pointer system with those blocks? And so that's how I ended up solving it. You can see here I created like a block type or a block structure, data structure, and I just say, hey, what type is it? What's the data in it? And how much of it is free? And then I can ask myself questions like, as I'm doing the two-pointer system and I'm right here, I can say, will 9 fit in here? And if it will, I'll shove it in here. And then my left-hand pointer will still be here. And now I can say, hey, will 8 fit in here? And if it won't, then I can just keep going through the free spaces and find it. And so that's actually what I do. And then I just have two helper functions here for the block to help me, fill up and clear out blocks, right? Because you can imagine I'm going to be filling these ones up and clearing these ones as I go through the problem. So what does part 2 look like? It's actually not much different. I still have to build it up, but now I'm building it up as a block, right? So basically I do the same filtering and mapping, but then instead of creating like the vector and using that to collect it up, I now just create a new block. And so now I have a list of blocks that I can iterate over from left to right and right to left. And that's basically just what I do. I start on the right-hand side, there's not the left-handed pointer happens inside this. You can see there's like 2 loops in here. I have a right side and a left side, and that's because like I want to start as far left as I can every single time to see if I can fit anything in there. Because in like this case, you can see eventually you're like, oh, I can fit the 2 in this space. So I always want to consult any free space that I can starting from the left side. And so that's why that's there. So I basically just say starting from the very right, move until I find a file, meaning it's not a free space. And then starting from the left, move through it until I find some free space that has room for it. That's essentially what this is saying, right? So if it's a file type, obviously there's not free space in there. If there's free space, how much is free, and do I have enough room to put the current file that I'm working on in there? And then I can just use those functions I did above to like move it over, right? And so I just keep doing that over and over again and slowly moving through all the files, and then eventually I've moved them over. So I've essentially done a two-pointer, like the two-pointer algorithm, 2 different ways. One over the like bytes of a file, and then one over the blocks, right, of like files and free space, and just done that to bring them together, and eventually you like find the free spaces. So to add this one up, I just do the same. It looks a little bit more complicated because I'm using a block now instead of the bits. So I have to like flat map all of the bits or all of the blocks into bits, but then I can just do the same thing and sum over it and get my thing. And you can see it does not take long. It takes 26 milliseconds. So it doesn't feel like it was ever a problem that was like, oh, I need to find some efficient solution for it. So that was day 9. What was the hard part of this? I actually don't know if there was anything particularly hard. Like the thing that was going through my mind as I was looking at it was, oh, is it going to be really big, and do I need to find some efficient solution? Like, for example, if you look at actual file systems, they actually usually keep indexes of this information, and then it's really easy for them to say, oh, I have a 9, where's my free space? Where can I put this 9 efficiently? And it will know, and it will figure out. And like your operating system disk doesn't usually go from like left to right. Um, if they're really smart, they actually try and span the whole file system and do it efficiently, right? Especially with SSDs these days. So like it may look like this, but when it's doing its like defragmenting or where do I place this file, they usually use indexes, right? They have these like trees or indexes that are tracking where the free space and the used space is. And so if you already had that information, you could potentially just, say, hey, give me the next free space that's this size and do that, right? And so my thinking was, do I need to implement something that crazy? Like, do I need to go look and see how, ext4 does its indexing or whatever, right? Which I was almost sure was not going to happen because it was day 9, but that was my concern. And it turned out to be just because, again, this is a thing you have to do, is maybe go look at the input and look at the data and determine how big of an issue this is. What's the complexity going to be, right? And so because I knew, it's only going to be like, the order of 100K items, this is definitely something that I can just like parse through, right? If I had done it and it said like, there's 2 billion, now you're in trouble, right? And now you need to start thinking about, an algorithm that's like that. I think this algorithm, because, well, part 1 is definitely just order n, because you're kind of just going like this, right? So part 1, I don't know that there's anything better than that. Part 2 is on the order of like n log n, because if you think about it, like for here you have to go for all of n, for here you have to go part of n. So maybe it's like, I don't know, n times n. It's like maybe like n squared over 2. I don't know exactly what the number is. It probably is n squared over 2 if I think about it. That's still not a terrible solution for a small number like this, right? Even if it was actually just n squared, that's not a terrible number to have to do. Where it would be is if you were in the billions, right? Suddenly n squared, you may say, can I find a more efficient solution that's like n log n or something like that, right? Anyway, it wasn't, so I just said to myself, well, let's just solve it like this, right? And it turned out to be 2 pointers. So if you've never seen a 2-pointer algorithm, I actually think I have videos where I've talked about this before, where especially like when you're using Windows and stuff like that, you may have like 2 pointers that describe the beginning and the end of the window. In this case, I had one giant window that was slowly shrinking over time, and you just implement it different way. At least for me, I just implemented it different ways for day 9. So there you go. I would love to see your solution and how you solved day 9. Maybe you've come up with some cool way to do it that was more efficient. Yeah, again, I thought of segment trees, and I think I saw a couple people said they used a segment tree. But when I looked at the solutions in the mega thread, I don't think I actually ever saw someone use a segment tree. I did see some people use a kind of an index, which is what I talked about with the file system, where they would say like, where are my blocks of free space? So they tracked you create the array, but within the array, you just have a list of free space. And then you start on the right hand side and just slowly fill up that free space. And so if you already have the index of free space, you can do an O1 operation to say, is there space, here, and eventually you find one, right? I guess not O1, but it's like, you're doing like a relatively simple search to find space that's available to you. So it's like n over 2, right? But again, the way I mean, mine's not much more inefficient. I start at the beginning and then I skip until I find space. I don't know how much that helps you. But I did see people do it that way, where you have a separate data structure that tracks the free space, and then you iterate over that. That maybe saves you time, especially on large things where like you don't have to, filter through the files every single time. And that's where it would be helpful, right? Is if you say you're always going to you're always going to do this while loop basically through the whole file system. Um, but this inner loop can be extremely if the disk size was really large, this inner loop could be extremely long and hard, and you'd want to maybe like tighten this up. Again, today's just didn't happen to be the case, so that was it. Send me your solutions. I'd like to see them in the comments or wherever. And I'll post all this stuff here so you can look at my solution. Feel free to fork it, and so I can see what you did, and just compare and contrast. If you have any ways to do things better, I kind of like doing this functional stuff, but sometimes I know it can be hard to read if you're not familiar with functional style programming. So if you found like another way to do that, love to see it. Anyway, you'll see another video coming up for day 10, and that should catch us up. We'll talk to you later.